I'm Sean Gannon, and this is Minute Math, and today we're learning about continuity.
Minute Math, when you need help you use Minute Math.
We're given this problem right here. F of x is equal to the piecewise function x squared plus 2x plus 1, where x is less than 1, and a negative x over 2 when x is greater than or equal to 1. And we need to find where this function is continuous. Now we're given a graph here of this piecewise function to help us out. Now it's continuous, right? It's continuous here pretty much almost everywhere, but there's something that happens at 1. Notice the open circle there at 1. That open circle shows that right there it is not continuous leading up from the left up to it. So it's continuous there from negative infinity to that 1 value, right, in the curve of the quadratic, but then at that 1 it is not continuous, okay? Now the second function, the second part here, says it equals to 1, and that's the straight linear line. It's continuous there at that value of 1, where an x is 1, all the way to positive infinity. And the reason here, the difference between these two right here, we're at the upper part where the open circle is, it's continuous everywhere up to that open circle, right there at that 1. But it's continuous at the closed circle part, all the way to positive infinity. Okay, so that's the thing to note there. So anyway, our final answer here is it is continuous from negative infinity to 1 with close the parenthesis there, and then a bracket from 1 to positive infinity. We're given this problem right here. F of x is equal to the piecewise function 1 when x is not equal to 5, but 3 when x is equal to 5. And we have to find when this is continuous. So our graph here shows what's really going on here. We have a straight line of y equals 1, but then at 5, or x equals 5, there's an open circle there. And up top, you have the point there at 3, right? And just really that one little dot there. So where is this function continuous? Well, it's continuous basically on all the real numbers except for 5. We can be continuous all the way up to that open circle right there, that open circle, everything up to that, but at that open circle it is not continuous, and at every point just after that open circle it's continuous. So we would say this is continuous from negative infinity to 5 and from 5 to positive infinity. So again, our final answer is this function is continuous from negative infinity to 5 and from 5 to positive infinity, but not equal to 5. We're given this problem right here. F of x is equal to the piecewise function 2x minus 10 when x is less than 2, and 0 when x is greater than or equal to 2. And we define where this is continuous. Now, I have a graph here for you that kind of shows what's going on with this function. We have a increasing line at the bottom there going up to when x is positive 2, then there's an open circle. Then on the x-axis, we have the line y equals 0 graphed, where x is equal to or greater than 2. So where is this function continuous? Well, it's pretty much continuous everywhere except for something happens at 2. The open circle, when there's an open circle on a function here, we can't say that's continuous there. So if we deal with just the top function first, we would say from negative infinity to a positive 2, it is continuous everywhere leading up to 2, except for 2, right? It can't be continuous somewhere where it doesn't exist right there. Now, the other part, y equals 0. Where is that continuous? Well, actually, right at 2, with the closed circle there, we would say that it is continuous there. And then it keeps on going forever to positive infinity. Okay? So it's a little tricky here, but this is kind of showing for the piecewise function where it's continuous. So again, open circle, not continuous, closed circle is continuous. So our final answer here is this function is continuous from negative infinity to 2, and, well, the parenthesis there, and then a bracket from 2 to positive infinity. We're given this problem right here. F of x is equal to x squared minus x minus 2 divided by x plus 1, and we define the intervals in which this function is continuous. Now, I have a graph here of our function. Now notice it's basically a linear line, but there's an open circle right there when x is in negative 1, which makes sense, because right there, if we put negative 1 in for x, we'll be dividing by 0, and it doesn't exist there, okay? So where is this function continuous? Well, it's not continuous at -1 because it doesn't exist there. But pretty much any other value leading up to that -1 from either side is continuous. So we would say that this function is continuous from -infinity to -1 and from -1 to positive infinity. But notice we have the parentheses around the -1 showing that it's not continuous there at -1. So it's continuous everywhere except for -1, and that is our final answer. We're given this function right here. F of x is equal to x squared over 2x plus 4, and we have to find where this is continuous. Now we have a rational function here, and the key thing with rational functions is really finding where it doesn't exist. And it doesn't exist in the domain there where we're dividing by 0. So I take my denominator, 2x plus 4, and I set it equal to 0 and solve. Subtract a 4 to both sides, pretty simple, and 2x equals a -4. Divide both sides by 2, and x equals a -2. So this is the key point for us here. This is really telling us where our function is continuous. Also tells us where it exists. And a rational function is pretty much the same thing. We're continuous from -infinity all the way to a -2, but not including -2, known as the parenthesis, then from -2 to positive infinity. And so my final answer here for where this function is continuous is from -infinity to -2, not including -2, and not including -2 all the way to positive infinity. We're given this problem right here. F of x is equal to the piecewise function -x over 2 minus 7 over 2, where x is less than or equal to 0. And from negative x squared plus 2x minus 2 when x is greater than 0. And we define where this is continuous. Now, if I ignore the domain for the moment here, both of these functions are just continuous everywhere. So we don't have to worry about that, right? There's no value for x that we can't plug in here. So it's basically continuous for everywhere. So the issue might be here, right, at 0. Now, one thing I want to check is what happens at 0 for each one of these values. I'm going to test. I'm going to see if they have the same exact y value when x is 0. So the first one here, so we're testing when x is 0. What's the y value? Well, when 0 goes in for x, that eliminates, and we're left with the -7/2. So y equals a -7/2. If I put 0 in for the second equation here, we get y equals a -2. And that's a little note thing for yourself. So notice the y values are different. So we have like a jump going on there when we transition at 0 here. So right there we know they don't have the same exact value, so I don't have to worry about that. So our first function, well, it's continuous everywhere leading up to 0, but including 0. So we would say this function is continuous from -infinity to 0, and it's including 0 because there's a closed circle there due to the equal sign. Then here, we jump to the second equation when x is greater than 0, but not equal to 0. So, parenthesis for the open circle from 0 all the way to positive infinity. And so our final answer here would say this function is continuous from -infinity to 0, including 0, and from 0 to positive infinity, but not including that 0. We're given this problem right here. F of x is equal to a -x squared minus x minus 12 over an x plus 3, and we define the intervals of where this function is continuous. One thing I notice here about these rational functions here is I'm really looking at the denominator, okay, where it does not exist. That's when we're dividing by 0. So I'm going to take this denominator, the x plus 3, I'm going to set it equal to 0. When it's set equal to 0 here, subtract 3 to both sides, pretty easy. And x equals a -3. So our function here doesn't exist when x is equal to -3. And what we know about rational functions here is that it kind of exists pretty much everywhere else. So we have here it's continuous here from -infinity to -3, then from a -3 to positive infinity, right there. But notice again the parentheses there at -3. Parentheses at -3 tell us there that it's not continuous there at -3, just every other value. And that's our final answer. We're given our function right here. F of x is equal to x squared minus x minus 6 divided by x plus 2. And we define on what intervals this function is continuous. Now, what we know about rational functions here is they're basically continuous where they exist. And, well, we're dividing by an x plus 2. So there's a chance here now that the denominator will equal 0. So let's go find those values. And it's more than a chance. X plus 2 equals 0. Subtract 2 to both sides. And x equals negative 2. And that tells us the value of x when we plug it into the denominator, where our function is not equal, is divided by 0, and therefore doesn't exist and not continuous there. So we would say that this function is continuous from negative infinity all the way to that negative 2. We'll put a parenthesis there at negative 2, showing not continuous there at negative 2. Then from negative 2 to positive infinity. And so again, our function is continuous for all real numbers except for at negative 2. We're given this problem right here. F of x is equal to a negative x squared over 2x plus 4. And we define if this function is continuous and what type of discontinuity if it's not, and where that is located. Well, right here, one thing I notice is that we're divided by something that could be a 0. So what I'm going to do is see where that equals a 0. So I have 2x plus 4, and I set it equal to 0 to find the x value. Subtract 4 to both sides, and we have 2x equals a negative 4. Divide both sides by 2, and x equals a negative 2. And that's really what's happening here. What's really going on is that negative 2, we can't plug that value in for x. Now let's look at the graph, roughly what it looks like. So this graph looks something like this. Okay, if I can give a quick little sketch here, this gives you a good visual. At negative 2, this graph does something like this. It has an asymptote there at negative 2, that comes up to the origin, and then it comes back down, and then it does something like this. Something like that, more or less, right? And then the x and y axis. And so this here is at negative 2 is where it's not continuous, right? Right there at negative 2. And we would actually call this an essential discontinuity. At what we have here at x equals negative 2. So essential discontinuity where it's like a big jump going on right there. And it's not just a little open circle there that's going on. So we have an essential discontinuity at x equals negative 2, and that is our final answer. We're given this problem right here. F of x is equal to x plus 1 divided by x squared minus x minus 2, and we define whether this function is continuous and things about it. One thing I like to do first is see if I can simplify this, see what happens if maybe we factor something out. Numerator stays x plus 1. The denominator, though, can factor to be an x plus 1 times an x minus 2. And this becomes crucial for us. We can see that the x plus 1's cancel. And this becomes a 1 over an x minus 2. So what happens there? Well, let's go look at a sketch of this graph. What's going on here? Okay? So right there at x equals negative 2, right, the denominator, if we put a positive 2 in, right, we, are dividing by 0, right, because x minus 2, we'll note here, equals 0, x equals a positive 2 there. That causes that denominator for the whole thing to equal 0. So positive 2 is where we have a crucial point. Our graph does something like this. Goes like that, and then it comes up here. That doesn't cross the origin, like this. But I'm not done with this graph, okay? We can see we have some disconnect right there at positive 2. But this value right here, the x plus 1, when we have that canceling out, that happens if we put a negative 1 for x, that part equals 0, and that would have worked for the original function. So if I put a negative at negative 1 right here, that should be an open circle right there. And this helps give us a visual of what's going on here. So again, we have if x plus 1 equals 0, x equals a negative 1. So here are the two values that where our function isn't really continuous, and we did classify them. Okay? So we would say at at negative 1, let's go with that one first, we have a removable discontinuity at x equals a negative 1. So the removable discontinuity that we're removing just that little point right there. We would say that we have an essential discontinuity at the other value, x equals a positive 2. So that's our final answer, removable discontinuity at x equals negative 1, and essential discontinuity at x equals positive 2. We're given this problem right here. F of x is equal to x plus 1 over x squared plus x plus 1. We define if this function is continuous, and, well, if it's not continuous, where is it not continuous, and the classification of the discontinuity. Now, this function is a little tricky. The first thing I always like to do is think, okay, well, when will my denominator equal 0? It's a key thing with rational functions. But now I'm in a little quandary, because this x squared plus x plus 1, does it ever equal 0? Well, we'll start seeing if we toss some values in. Toss 0 in, no, right? Clearly goes out. If I put a negative value, negative 1 in here, we'll have a positive 1 right here, oh, but not equal to 0. What about if I put more and more negative numbers in for x squared, this value here, put negative 2 in, right, for x squared, well, that's being positive 4, cancels out here. And that plus 1, all this whole thing, this function actually never touches the x-axis. It never equals 0. So that's something, if you need practice, you also use a quadratic formula, and you can find that it's an imaginary solution. But it doesn't equal 0. So what happens here? Well, our graph looks something like this. I'll give you a quick idea of the sketch. It does like this, kind of comes down, comes up, and does something like that. Something like this, right? Doesn't really matter. It's continuous everywhere. So the denominator will never equal to 0. There's nothing that causes this function to actually be not continuous. And so we would say that this function is just continuous. And that is our final answer. We're given this problem right here. F of x is equal to a negative x squared over x minus 1. And we define if this function is continuous, and if it's not, well, where it is and what type of discontinuity it is. Well, I look at this denominator right here, and I know it's crucial that if we're divided by 0, we're not continuous. So I take the x minus 1, I set it equal to 0, and clearly, adding a 1 to both sides, x equals a positive 1. And that's where my issue happens. Now we can see a sketch of this graph right here. I'll look at a visual. Right here at positive 1, we have a vertical asymptote there. Our graph does something like this, kind of comes in, goes up there, I think it touches the origin here, and then it does something like this. Something like that. I don't know if it does that shape, but it doesn't really matter. Right? At 1, there's an issue, right? It has this thing. The 1 doesn't cancel out with anything in the numerator, and so we actually have what we call an essential discontinuity going on. And that's what kind of that looks like. So we would say that this has an essential discontinuity at x equals a positive 1. And that is our final answer. We're given this problem right here. F of x is equal to the piecewise function of x squared minus 4x plus 3, where x is not equal to 0, and 3 when x is equal to 0. We define this function as continuous, and if it's not, where is it discontinuous, and classify the discontinuity. Now, what I notice here, if I ignore the restriction on the domain, both of these functions are continuous, okay? So really I'm looking at, well, continuous forever, right? But I'm only looking at here at 0. That's the crucial thing, okay? Well, what I'm actually looking for is seeing if they equal the same value at x equals 0. So the numerator, or the top function here, what happens when x equals 0? 0 squared minus 4 times 0 plus 3. What does that equal? Well, 0 squared, 0. 4 times 0 is 0. We just get a 3 here. And this one always equals 3. So this actually has the same exact value. So what does this look like on a graph? So we have a quick sketch here. We have a parabola here. And our parabola of our function kind of does something like this. Now don't hold me to any close values here. This is a sketch. But right here at 0, right, we have what we call an open circle. When x equals 0 at positive 3. See, it could be a little higher, but it's okay. Right there at x equals 0, an open circle from the top equation. But that hole is filled by the second equation right there at 3, that one little point, as such. And so with that information, this function is actually continuous everywhere. So this function is a continuous function. We're given this function right here. F of x is equal to the piecewise function negative x squared when x is not equal to 1 and 0 when x is equal to 1. We have to see if this function is continuous, and if it's not continuous, find the x-axis location of the discontinuity and classify it. Well, one thing we know, if we don't have the domain restricted, both of these functions are continuous. Okay, they're both continuous functions. So what really is going on here? We have to figure out what happens really at that one value. So let's go take a little sketch of this graph here. It should be pretty easy to do. Our top function, negative x squared, we know is an upside down parabola, like that. But they tell us that at x equals 1, let's say this is equal to 1 right here. At x equals 1, it's not equal to 1, right? We have an open circle right there. That goes on. Now, they say the function at that value is equal to, well, equal to 0 when x is 1. So we have a point right here. Okay. So this one's a little tricky here. Okay. We see that we have an open circle right there, and that's where the discontinuity happens. So we would say that this actually has a discontinuity right there at x equals 1. But what type is it? Well, if you look at our original function, it exists everywhere, and we're just removing that little hole out of there. So, hint, this is a removable discontinuity at x equals 1. And so our final answer here is that we have a removable discontinuity at x equals 1. We're given this critical thinking question. Give an example of a function with discontinuities at x equals 1, 2, and 3. Now there are many answers here that work, but mainly here I'm trying to find discontinuity, and the best way to do that really is, well, divide by 0, right? When our function divides by 0, and make that happen when x is 1, 2, and 3. So again, there's many answers, but if we say f of x is equal to 1 over here, watch this. If I put an x minus 1, I plug 1 in, that denominator equals 0. I do an x minus 2 next to it, plug 2 in, we're dividing by 0 again. And lastly, x minus 3. Put a 3 in for x, that becomes 0, we're dividing by 0. And so that's it. There are many answers here for this final function, but here's an example of one. F of x is equal to 1 over x minus 1, x minus 2, x minus 1 times x minus 2 times x minus 3 is an example of a function with discontinuities at x equals 1, 2, and 3. We're given this critical thinking question of the 6 basic trigonometric functions which are continuous over all real numbers, which are not, and what type of discontinuities are there. So the first thing I'm going to look at, I'm just going to think about the 6 basic trigonometric functions: sine, cosine, tangent, cosecant, secant, and cotangent. Those are the basic 6 there. Well, which ones are continuous? Well, the only continuous ones I know of are the sine and the cosine. Sine and cosine have a basic shape like this, right? Can I go on forever? And that's like the basic function. Forever, up and down, and it's continuous everywhere. All the other ones are actually not continuous. That would be the secant, and notice I'm putting a lot out of order here. Cosecant, and the tangent, and the cotangent. Well, the secant and cosecant have basic shapes like such. It has some like U things that go on like this, right? And the tangent and cotangent have some basic shape where it's kind of like It does sound like this, right? Well, what type of discontinuities are these, right? Well, these, we have a big gap that's going on. It's like asymptotes here that are happening, and jumps, really. So this, or not really jumps, this is just asymptotes that are happening that are causing this discontinuity. So this would be what we call an essential discontinuity, and that's the classification of the discontinuity. So again, our final answer, the continuous functions are sine and cosine. The not continuous functions are secant, cosecant, tangent, and cotangent. But we can see, like I said, the graphs right here. And the type of discontinuity that is an essential discontinuity for them. I hope this video was helpful for you, and if it was, please subscribe to this YouTube channel and like this video. This helps us make more free math lessons for you and for everyone else. So as always, thanks for watching.
Minute Math. When you need help, you use Minute Math.